Okay, so let's get started. 1 second. Yeah, so let's get started. So today, in the last few classes, we, kind of looked into the wave equations and how the wave equations kind of come into picture while we are going to model the transmission medium and in terms of electrical impedances. So the medium part, meaning understanding the medium of transmission, or the method of transmission by sound waves and how it behaves when it is propagating from one medium to other, all that we discussed. And we'll keep the medium aside for some time and then go back to the the piezoelectric crystal to understand how we can make it work as a transmitter and a receiver, right? Because only then we will be able to make the complete system of ultrasound. So as we understand that, of course, we will look into the details of the ultrasound electronics as well. And we use ultrasound for medical imaging that I think you people must be aware, based on common knowledge, nothing to do with the subject by itself. So if we think of a transmitter, right, we can model the transmitter as a two-port network, right? And because we are talking of transmitter, essentially what it means is we are able to transmit a signal from one domain to the other. And because here we are talking of like ultrasound, the input we are electronics engineers and we will talk from an electronic signal perspective, right? So the input we are going to give is an electrical signal, right? So it's a two-port terminal, port 1 on the input side and port 2 on the output side here, right? So when we apply a voltage, there will be a current that will be flowing into this two-port network. And at the output, because it's a transducer, we will expect a force or a displacement. So please note that the voltage on one side and the force on other side are kind of synonymous. And similarly, the current on terminal 1 is synonymous to the displacement in the terminal 2, right? And this kind of makes sense because we have looked into how from the electrical domain we can go into the mechanical domain and vice versa. And of course, because it's a transmitter, this is also understandable that we are going to talk of the inverse effect, right? Essentially, we are giving an electrical signal and we are going to get a output in the mechanical domain, right? So how do we model this? So sorry. So if we model this, so we can say that, look, we are applying a voltage across a capacitor. So the piezoelectric crystal that we had seen, right, that yellow colored cube, it had two metallic plates opposite to each other, right? So we can say we are applying a voltage across those two plates, which means we are applying a voltage across a capacitor, and then a current I will be flowing right across, on the capacitor plates, and based on the current that is flowing or the voltage that we have applied, in other words, the voltage that we have applied, we are modeling the output side. Please note that this model on the left hand side is my electrical input signal that I'm giving. On the right hand side, I'm obtaining what? A mechanical signal in terms of force or displacement, right? So how can I model, so if it's a two-port network, on one port, on the left-hand side, we are applying an electrical signal. On the right-hand side port, I will get a mechanical signal based on some parameters. And what are the parameters that we have kind of, we understand by now? So if you see here, we have applied a voltage V, and what I have put here is essentially nothing but a voltage controlled voltage source given by dkV, right? Where D is a piezoelectric constant, K is the mechanical property, and V is the voltage that we have applied, right? So this we know pretty well by now, right? I mean, why it is going to be dkV. So based on the voltage that we apply, we are actually generating a strain in the crystal. So let's say the crystal is free to move, right? I mean, the crystal is free to deform, and the strain that we are generating is proportional to the voltage that we have applied. Any questions up to this point? This we have discussed, right? Now, what is the value of C, L, and R? So what is the value of C, L, and R? So that also we have derived in the previous, classes. But before we, we'll go back to this, what is the value of C, L, and R? But before that, let's quickly look at it. So this is our strain, equation relating strain to the electric field that we have applied, right? So strain, I can just write as X divided by the length, the actual original length of the, one second. So strain is nothing but X is the deformation that is happening over the length. So this was, if you remember, our crystal was like this, right? Length or thickness, whatever. And let's say we are applying the voltage across these opposite faces of the crystal, right? So the deformation that we got, the strain, if I divide this by L on both sides, if I can write this by X by L, and electric field is also nothing but V by L, right? So the L cancels out, and the same equation, S equal to dE, this I can write in very simple, more relatable terms, as X being the deformation and V being the voltage that we are applying. And X again is proportional to the force or the stress that, or you can say the force that is actually being built up in the system, right? The stress that is being built up in the system, right? So from that spring and the damper model of the crystal, we had a spring and the damper model, right? If you remember, there was a spring and a damper model. We had a mass M and we applied a force F, right? And if you remember, we had derived the transfer function of this XS, where X is the deformation, the X is the movement from the equilibrium position. XS by Fs we had derived earlier. It was given by 1 by K in, it was a second order transfer function, right? Omega n square and 2 epsilon zeta by omega n S plus 1. So this was what we had derived earlier. And we had derived this from what equation? From by simply equating the force with, so this is the force that we are applying. So we, so if we just write in terms of the mass and the spring constant, so this was the spring that we had K and the damper C, right? If we wrote, so this was nothing but 1 by ms square plus cs plus K, right? K was the spring constant, C was the damper coefficient, right? And M was the mass, right? So from this we had, if you remember, we had equated the second order transfer function to a equivalent inductor, capacitor, and a resistor, right? So now please note that we are talking of X dot here, not X. So because it is X dot, in I think one of the previous slides also, we had shown same equation. If we just write in terms of X dot instead of X, X dot S was what? That could be written as MS plus C plus K by S, right? Just simple force and the displacement equation, right? So the same, so basically the force, the internal force or the stress that we are generating, if this is the force F, right, that we are generating because of applying a voltage here, right? So we can, if you see here, we have a VC voltage controlled voltage source. What it means is the voltage that will appear in the mechanical domain is proportional or controlled by the voltage that we are applying on the terminal 1, on the port 1 of this 2-port network. So this is clear, right? Any questions up to this point, right? So basically what we are saying is this dkV. So this is F is equal to dkV. D is the piezoelectric constant. K is the spring constant of the equivalent spring constant of the material. and V is the voltage that we are applying, right? So this is dkV. Any questions up to this point? So, and this will come. So this is the total force that I am getting, which is, as I mentioned, this is synonymous to the voltage that we are getting on terminal 1. The force on terminal 2 is synonymous to the voltage that we are applying. So if we add, so what is the overall force that we are generating across the piezoelectric crystal? That will be given by this voltage control voltage source, and the output impedance will be given by R, L, and F. So if you kind of write what is the overall force on this, right, this will be given by dkV, right, minus, right, if I look at the equation from this side, right, so the overall force that I'm generating will be dkV minus x dot times R, right, and then ls x dot plus x dot by CS, right? So this is the overall force that we are generating. This is again from the same, spring and the damper model. So this is clear, right? So if this is the force that we are generating, and this is the displacement that we are generating, so we are saying that our transmitter, equivalent transmitter, and where are we going to apply this displacement? If we see in an ultrasound, right, we have a piezoelectric crystal. On one end of the crystal, we will give a voltage signal, and this displacement will happen where. So let's say in the car, when you are talking of ADAS systems, right, wherein you are detecting an object lying somewhere nearby, right? What we are doing, we are generating sound waves, and the sound waves, if we go back to this this thing, right? We talked about how the transmitter and the receiver system works. That we have a transmitter which emits the sound waves, and then we also, the reflected sound wave is gathered by the receiver, and then we do the electronic processing of it, right? So again the same, the value of the resistor, the value of the inductor, the value of the capacitor, we know, right? And this F is the final force that we are getting across the terminal, right? So this is how we can model the transmitter, a very simplistic model of the transmitter. So now let's look at the two-port network model of a receiver, right? So the two-port, when we are talking of the two-port equivalent model of the receiver, we are talking of the direct effect, right? Because we are applying a mechanical signal at the input, and we are getting a electrical signal at the output. Please note, whatever parameters or the signals appeared on terminal 2 for the receiver, for the transmitter, the same parameters are appearing on terminal 1 for the receiver, right? That's how it should work, right? We apply an electric signal to the piezoelectric crystal, and then we get a mechanical signal output. And when we are receiving, again, going back to the previous slides diagram, right? The sound waves, when it is reflected back, sound waves are nothing but pressure waves, right? Which will create, the pressure waves will create a displacement. It will put pressure on the piezoelectric crystal, which will create displacement in terms of, like, it is going to, create small deformation on the piezoelectric crystal, and that can be treated as the input to the receiver, right? And the output, because it's in the direct effect, right? In the output, we will get an electrical signal, right? So this is how the receiver can be modeled, right? Any questions up to this point? Just that we are representing this as a two-port network, right? And when we are going to, how we are going to represent the receiver in electrical terms, again, the same stuff, whatever kind of, if you see here, whatever appeared here is appearing here. There is only one change, because this was a transmitter, and so we had a voltage control voltage source, which was dependent on the electrical signal that we are applying on the input terminal. Here on the output side, we have so what will be this? What will be this, guys? This we have discussed, right? for a piezoelectric crystal, if we apply a force, what will happen? That there will be charge that will be accumulated across the plates of the capacitor, across the terminal of the piezoelectric crystal, right? So essentially, if you see how we are modeling this two-port network when we are talking of a receiver, is we are creating a displacement x dot, and of course the same capacitor, inductor, and resistor. This you guys should be very aware of now, right? So which we had derived this earlier in the earlier class also, right? So based on the displacement or the force that we are having, we are creating across the input terminal. This is nothing but a current control current source, right? I can say that this is a current control current source. And what is the, what is the why dkx dot? Why is it dkx dot? Just like here I had written dkv. So this came from the fundamental equation of the strain equation, the equation relating strain to the electric field, S equal to dE, right? So similarly, when we are talking of the direct effect, we know the polarization P is proportional to the stress that we are applying across the piezoelectric crystal. So polarization is nothing but the charge density, which is Q divided by A. So basically, if I write this right, this is Q divided by A, and T stress is also nothing but force divided by area. So I can cancel out the area on both sides, and I can rewrite P equal to dt as simply Q equal to dF, and F again, if I replace F as Kx, right? F is equal to Kx very simplistically, right? The force that we are applying, if it, we are just replacing, the displacement that has happened, right? Or the deformation that has happened because of the force, right? Is F equal to Kx. Please note that this is the steady state equilibrium displacement that we have created, right? The S square and S terms doesn't come into picture here when you are denoting it like this, because those terms are hiding here, right? Those terms are hiding here, right? So F is equal to, basically we're talking of the force in the equilibrium state that we have generated, and that is nothing but Q equal to dx, the total deformation that we have created, right? So I taking differential on both sides is nothing but dk x dot. So this is the current source, equivalent current source, that is going to dump charge onto this capacitor, right? And this capacitor is going to create a voltage which we are going to kind of read out into our electronic system. And then if I can read out this voltage, that means what? Essentially, I'm reading the force that has been applied on the input terminal of the receiver, right? So basically, based on the fundamental parameters of L, R, and C, and by understanding the way the crystal behaves, it is fair to derive this kind of a two-port equivalent model for the transmitter as well as the receiver. The thing to note is when we are talking of the transmitter, we are talking of the inverse effect, which we are now very aware of. And when you're talking of the receiver, we are talking of the direct effect. And the other thing to note is when we are talking of the transmitter, we have a voltage controlled voltage source, and this voltage source, the value of the voltage source is dependent on the input terminal. So does this kind of a two-port terminal, does it remind you of some device that you would have studied maybe in second year or the 5th semester? Does it remind you of any device, guys? So any electronic device in your electronics course, does it remind you of a device? Any? Does it remind you of something?
Is it like
any answers, guys?
BJTs and MOSFETs are also modeled like.
Yes, absolutely. So BJTs or MOSFET. So BJTs is actually a current control current source. And if we talk of a simple NMOS MOSFET, right? If we talk of a simple NMOS MOSFET in saturation, if we draw the small signal equivalent of that, of this NMOS MOSFET, how do we denote that? We denote. So this is a current and this is an output impedance. And this is port 1, which is nothing but gate and source. So this is in a common source configuration, right? We're talking of a common source, and I had discussed what is common source and all that. So, and this is nothing but a voltage controlled current source. And this current source, the value of the current is dependent by a coefficient Gm. We know we can derive what is Gm, and whatever voltage we are applying here. So let's say V in. So the current source I will be given by Gm times V in, right? And of course, this is the output impedance R0, and this also can be derived in terms of the operating condition, right? So if you see, right, this is precisely, I mean, whatever we have derived here, just that this is also a two-port network, just that the output port or the port 2 on this side is represented in mechanical terms. That's the only difference. But otherwise, this is also a two-port network, and we can actually derive the two-port equivalent model. If we, if we talk of a, let's say the admittance matrix or the impedance matrix, we can derive the matrix of this kind of a two-port network. We can do that, right? Any questions up to this point? So this is clear, right? How we can model the transmitter and the receiver. This is clear, right? Any questions, guys? Please feel free to ask. Okay, no questions. So let's model the complete transmission path, right? Let's do that. Now that we know that this is how the transmitter is going to look like, right? So we are going to apply the voltage by some, by some voltage source or a signal source, right? And how can we represent a signal source? We can represent a signal source by a signal generator, right? And this is the signal source. And what is ZS? ZS is the output impedance of the signal generator. And similarly, on the output side, which is nothing but, because it's a transducer, the output signal again is going to be in mechanical domain. We are talking of the inverse effect here, right? We're applying an electrical signal in the input port, and we expect a mechanical signal at the output port. And where does the mechanical signal go? It will probably go into a fluid, meaning it can go to air, or it can, the sound waves that we are generating, right? That will actually go, I mean, let's say if we are talking of a ADAS system of a car, where the beep, beep, beep sound comes, right? Based on the nearest object that it is detecting. So there, in that case, the medium will be air. Or if it's for medical applications where, you see the doctor, taking the ultrasound and a machine and then putting it, on the skin of the patient, right? In that case, the medium can be blood, right? I mean, it can be any biomedical kind of fluid, right? So this X dot will be flowing into a medium with a certain acoustic impedance. And we have talked about the characteristics of acoustic impedance and how it is, I mean, how this acoustic impedance will be dependent on the characteristic physical properties of the material that we have discussed in the previous slides. So this can be the overall transmitter model comprising of the signal generator. This is the piezoelectric crystal on this side, and then this is the medium where the sound waves are going to be transmitted. Okay. Any questions on this? This is a complete model from the transmitter side. And what will be the complete model on the receiver side? So whatever waves we have transmitted from a transducer, those waves will be reflected and it will be received back by the transducer. And depending on the configuration, it can be, and we'll talk about that, whether it will be the same transducer or it will be a different transducer. So those are configurations called as monostatic and bistatic. We'll talk about that later. But the sound waves that need to be studied will be reflected back from the object, or it will be actually propagating through the medium, and it will create. So we can treat those sound waves as a source, as a mechanical signal source, and with the output impedance depending on the, again, the output impedance here depends on the medium we are talking about, right? In this case, if it's a car, again, it can be air. If it's, it can be a biomedical fluid, or it can be anything, right? But we does need a medium, right? So the medium has acoustic impedance. So we can model the sound waves being as a, signal source with an output impedance given by the medium in which the signal is, or in which the sound wave is propagating, and that creates a displacement x dot. It creates a displacement. I mean, x dot is essentially the rate of change of the deformation in the crystal. And this in turn creates a charge that this is actually a current source which we discussed. This is the the receiver model that we discussed, right? And this charge will be, creating a voltage kind of a signal at the output. And this voltage is what we can read back. And then we can get information about, the speed of the, we can get about, information about what kind of waves have been actually, given as an input, right? So now, and similarly, so this is the readout circuit. So nothing big in this, right? This is our impedance offered by the, we'll have some readout circuit in the lab also you did, right? There will be an op amp and, the charge mode amplifier and all that stuff. So that will offer some impedance to this voltage source. So this is clear. So this is how the ultrasound receiver is going to look like. See, we are doing everything in parts. First, we understood based on the sound wave equations, we understood how the medium is going to behave and what will be the relation of the pressure and the displacement of the pressure. When we studied the the medium, we looked at the relation between the pressure at a particular location x, and we looked at the particle displacement, and we looked at the fundamental relation relating pressure, the particle displacement, or the velocity. We looked at that, right? And then we talked of acoustic impedance. So that was one part when we studied the medium. The second part is now we have studied the model of the receiver and the transmitter. Now the third part is we will be looking at the whole system together in one shot, meaning now we are ready to understand if we have to create or design an electronic system around transducer. We know all the basic components. We know how the medium is going to behave like. From understanding the piezoelectric crystal, we know how the transmitter is going to behave, meaning the equivalent model of the transmitter we know. And similarly, the receiver, whatever signals it's going to receive, will create some voltage, and that we can. So now we are ready. We know all the basic building blocks of an ultrasound system, right? Any questions up to this point? Okay, so this now will be the overall transmission link. So this is how an overall ultrasound system is going to look like. And ultrasound, by the way, is a very important, a lot of active work is going on ultrasound imaging. Like if you want to go for higher studies or if you join the electronics industry, you may end up actually doing this kind of system design. So it's important we understand how the systems are modeled by understanding each part comprising of the system. So for example, here, the signal source will be, you as an electronics engineer, most likely will be designing the signal source and the readout. This is what you will end up designing, right? As an electronics engineer, if somebody is working in the fab who is designing the crystal, right? He's going to, let's say, decide what is going to be the thickness of the crystal, what sort of material we are going to use based on, the coefficients that we talked about, right? The strain, the different equations that we talked about to obtain the best possible coefficients. So your friend will be probably designing the crystal itself, right? And then we need to understand the physics of how the waves propagate, and then only we will be able to design the full system, right? So this is the overall transmission link. We understand how the transmitter is going to behave, the receiver is going to behave, and also the transmission medium. This is what we did so far. Let us go a little further. So what we are seeing here, so let's say I'm saying that this is my x equal to 0, right? Meaning this is where the sound waves are being generated from the transmitter. So this I define as x equal to 0, and the sound waves will be propagating and hitting the receiver at a length which is at a distance Lm, right? So basically why Lm? Because this shows the length of the transmission medium. So the length of the transmission medium is Lm. So at x equal to Lm, we have a receiver, right? So if we see here, we have three components, right? We have the transmitter, the first component. which is actually injecting a sound wave because it is vibrating the particles in the medium here, and the waves propagate and it applies. So this is the force that the crystal is applying to the particles in the medium, and the waves will propagate. Of course, there will be absorption at this absorption and transmission at this edge, and there will be absorption and transmission, reflection or transmission at this edge. All that we already saw when we were looking at the wave equations. Any question? Gunjan, any question? Okay. So so then we have the sound waves propagating from this edge to this edge, right? So then what happens? I mean, let's try to put some mathematics into all this. So let's say the power that is incident on this transmission medium, let's say that is given by WT, right? So this is the power that is incident from the crystal on this medium. Now, based on the wave equations that we have studied, we know that there will be a transmission coefficient when the sound wave is going from medium 1 to medium 2. And let's say that coefficient I'm denoting as alpha t. Alpha t, we have talked about alpha t earlier. If you remember, we derived, what is alpha t? I mean, and we said that this is 1 minus alpha r, and we had written that this was 4 R1 times R2 divided by R1 plus R2 whole square. When we looked at that wave equations, right, we have derived all that, right? And if you want, you can refer back to the previous slides. But the point is, if we are applying, a power that is incident at this interface created by, given by the crystal, if this is WT, right? So the power that is going to enter the medium is going to be not the full power, but it is going to be multiplied by a transmission coefficient alpha T12. And why have I written 12? Just to show that the transmission coefficient, when the wave is propagating from medium 1 to medium 2, this is going to have a particular transmission coefficient, which will not be the same as alpha 23. It may not be the same when the wave is going from medium 2 to medium 3, right? So alpha T12 is what I'm writing. So the power that is coming from this edge is not going to be the full power, right? There will be some loss. Why will there be some loss? Because some of the power, incident power, that is incident on this interface medium, some of it will be also reflected, right? And that coefficient is given by alpha r. So we are not talking of alpha r here, because finally we are interested in how much power we end up receiving at the receiver here, right? That's why we are not talking of alpha r here. We are interested in alpha T12, the transmission coefficient from medium 1 to medium 2. And similarly, another thing that we had seen, when the sound wave is propagating from one point to another in space, we know that the power or the intensity is going to decay with distance. That equation also we have seen, right? It was an exponential equation where if the power that is incident here at x equal to 0 is this alpha T12 Wt, because the wave is propagating a distance of Lm, there is a loss in the medium, right? And that power loss, eventually the power that will reach this interface is nothing but e to the power alpha W2 Lm. Why W2? Because this alpha W2 is a property of this transmission medium. This equation also we had actually seen. Right? So this is the amount of power that is incident on this interface between 2 and 3. Now we will talk of. So this is the power that is incident at this is nothing but whatever power. This was the input power to the transmission medium, and the output power is equal to the input power multiplied by the exponential decay. There has been a decay, and some portion of it only reaches this interface. So this is multiplied by e to the power alpha Wt Lm, and this decay is also proportional to Lm, right? That the distance that the wave has traversed. We had seen this equation in the when we discussed the wave equations. We had discussed these phenomena. I'm not going back into that. And then, so this is the power that is incident on this interface. The power that is finally received by the receiver is this guy multiplied by another coefficient, transmission coefficient alpha 2, 3. As I said, when the power that was incident on this interface, not the complete power was not transmitted into the medium, some portion of it was reflected, and the portion that was transmitted was given by a transmission coefficient alpha T12. Similarly, the power that is received by the receiver is not the full power incident at this edge. It is proportional. Some of it will be reflected back and some of it will be transmitted. And what will be the thing that will be transmitted? That is this power multiplied by alpha 2, 3. So this is the final, power that the receiver is receiving after, all these losses alpha given by alpha T12, given by alpha omega, W2, and then alpha T, finally alpha T23. So this is the overall. So you gave some power, right? When you actually threw this electrical signal, you actually generated sound waves with a certain power or a certain intensity, but not all of it reaches the receiver. Only some portion of it reaches. So this is the overall equation. The power that is finally being received by the receiver is given by this. Any questions up to this point? Okay. So, so now let's take a closer look and what is actually done. So now, as we know that between the transmitter and the transmission medium, or in other words, also the transmission medium and the receiver, right? There is a power loss. So typically what is done is we actually put a matching layer between the transmitter and the transmission medium. And why do we put the matching layer? That is what we are going to discuss now. So we have, so instead of the interface 1 and 2, we have now introduced another matching layer. In order to have now two interfaces, the sound waves are now going to pass through from medium 1 to medium M here, the matching layer, and then from medium M to medium 2. And this is done to, with a certain goal. And the goal is to ensure that maximum power is actually transmitted from medium 1 to medium 2, meaning the reflection is minimized. So let's try to see what sort of characteristics, acoustic characteristics, this matching layer should have. So if this is WT, as we discussed earlier, so here the amount that will be transmitted into the medium M is given by nothing but the transmission coefficient between 1 and M, WT. And similarly, the power that will be finally reaching the transmission medium will be given by the incident power multiplied by another transmission coefficient, which is given by alpha T M2, right? So the effective transmission coefficient that we have from medium 1 to medium 2, instead of alpha T12, which we discussed in the last slide, instead of that, the effective transmission coefficient is nothing but the product of these two numbers. So this is clear, right? A straightforward thing. And so this kind of tells us, why, this matching layer is being put. That's what we are actually trying to understand, right? So effectively, the effective transmission coefficient from medium 1 to medium 2 is given by this, right? So now, so if you remember, alpha T that we had derived from the wave equations was given by 4 R1 R2 divided by R1 plus R2 whole square, right? For two mediums having impedance, acoustic impedance R1 and R2, right? We had derived this earlier. And we also know what are the physical characteristics based on which the acoustic impedance R1 and R2 are going to be dependent. So if we now, because we have two coefficients now, right? So this will be the overall. This will be the overall transmission coefficient from medium 1 to medium 2. So what is the variable that we have here? We will not be introducing any matching layer, right? We will be carefully choosing we'll be carefully choosing a particular matching layer which is going to ensure that alpha T12 is maximized. We have to maximize the power going from the medium 1 to medium 2. And that is the goal, right? So this is like a variable medium that we are introducing to ensure that most of the power is transmitted from medium 1 to medium 2. So Rm is my variable. So if I do the calculus, and I mean, if I take the help of calculus and if I try to see, when under what condition of Rm will be this effective coefficient be maximum, we'll figure out that this will be maximum when Rm is the geometric mean of R1 and R2. So this is an important relation. This is a geometric mean of R1 and R2. So basically, while choosing the matching, so PVDF essentially is a biocompatible. In medical, so if let's say this is the ultrasonic transducer, and let's say this is blood or skin, right? So typically, as a matching layer, the doctor will either put a gel or something like that, right? Or PVDF is also a biocompatible material which can be used as a matching layer to ensure that the coefficient of transmission from medium 1 to medium 2 is maximized. Any questions up to this point? Okay, so now this is how the overall ultrasonic system is going to look like. We are going to get back into the actual, the waveforms or, what sort of scans are doing. So this is a little bit of a large slide. We need to understand carefully that if as an electronics engineer, if you open an ultrasonic system, what all things you expect to see. So let's start from the power supply, right? So of course you will be plugging it into the power supply of whatever or 220 volts or if it's in US it will be 110 volts and the frequency from 50 to 60 hertz or whatever. And then we have an AC to DC supply. So basically this overall thing, and we have a voltage supply voltage supervisor, so which will check what is the supply voltage level here and all. So essentially this is a power supply system. So nothing. I mean, this is of course a separate domain, but we are not talking of this. But let's look at what else is there, right? So this power, this power module is going to give, it's going to power this whole complete electronic system. So if you see here, the transducer or the piezoelectric crystal sits right here, and this system, what we are showing is the same transducer works as a transmitter as well as receiver, meaning by exciting this crystal with with pulses, voltage pulses, we can generate sound waves from the transducer. And also when the sound waves are incident on this crystal, we can use this as a receiver, right? And whatever we are going to receive can be amplified. It will go through a certain electronic signal chain, and we can read what is the signal that we are receiving, right? So if you see here, for the transmitter, we need voltage pulses. So because only then, that's what, if you look at that transmitter model, what was the input signal we had was a voltage pulse, a voltage signal, right? So that is being driven by an integrated high voltage pulsar. We're going to look into each of these, how it is going to look like, but let's try to understand the block diagram. So this guy will be driving the transmitter when it is in the transmission mode, right? Similarly, so these are transmission or receiving switches. So when this transducer is working as a receiver, what happens is the electrical signal will flow through these switches, and it is going to go to a LNA. What is an LNA? It's a low noise amplifier, because the sound waves that are being received by the transducer will create small voltage signals which needs to be amplified. And why it needs to be a LNA, low noise amplifier? Because the signals that are generated will be in the millivolt range, and the noise of the amplifier itself should be much smaller than the signal level, right? Otherwise the SNR, the signal to noise ratio, will be messed up. So we need an LNA right at the beginning here. And then from after the LNA, we have a variable control amplifier. The gain of the amplifier can be varied. And this again, there is another PGA, programmable gain amplifier. We'll not discuss too much. I mean, we'll see how each one of them looks like, but then it is important to understand the signal flow. So after the LNA, so this is for the receiver side. After the LNA, we have a variable gain amplifier. Now the pulses that we are going to receive needs to be filtered, right? Because there will be noise and there will be unwanted interference from other sources which needs to be filtered. So we'll need an low pass filter, and then this needs to be given to an ADC, which is going to tell us, it's going to digitize the voltage signals that we have read from the transducer is going to be converted into the digital domain. Again, will go into the, so if you look at the ADC, right? So this guy goes into a digital, you can say this is the DSP, so this is the back end. So this is a digital signal processing unit where based on the voltages that you have received, we can do further processing of the signal. And then you can see, there are other things like this audio output. If you are actually trying to listen, or you can see the signal through a monitor, whatever signal that, either you can, so that beep, beep, beep coming from a car, right? That is an audio output. Whereas if you want to, see it in a display, that also can be done. So this is where the digital signal process. So if you are a digital design engineer who will be designing, let's say, the digital filters, you will be dealing on this portion. And if you're an analog design engineer or a circuit design engineer, you will be dealing in all of this, right? Designing the LNA, the programmable gain amplifier, the low pass filters, and all of this, right? So this is, and similarly, if you see on the transmitter side, what happens is again the same digital guy, and you will see why there is a correlation between the receiver and the transmitter. It is kind of understandable because you are using the same transducer to actually transmit the signal as well as receive the signal. So we need to know, which we'll discuss, why there has to be, why this guy, the transmitter, needs to know that I'm in the receiver mode or I'm in the transmitter mode, and whether you want to turn on this path, the transmitter path, or the receiver path is controlled by the digital signal processor. This knows now I need to turn this guy off, the receive path off, and I need to send a signal to the transmitter. So this is the reason why you see that the integrated high voltage pulsar also gets a signal from the digital domain, and it knows that, okay, this is what I need to do. There is a DAC and all this we are not going to talk about, but it's important to understand the signal flow. So this is clear, right? This kind of gives us an idea what all things are involved in an ultrasonic system. It's a very high level view, but it's important to understand that, okay, if this gives you, and by the way, these are very modern systems. These are like state of the art systems. If you are going to work in this domain, you will see these kind of systems being designed. Okay. So how does the pulse ecosystem work, right? Pulse and ecosystem work. So what happens is, and this is from this slide, you are going to understand why the digital signal processor needs to talk both to the transmitter as well as the receiver. So what is done is, first, we generate a voltage pulse. We transmit a pulse of a certain width, TW, and of course, a certain voltage level is provided. And higher the voltage level, and we are going to see in a graph later on, higher the voltage level, more will be the sound pressure level. So if you do the sound pressure level SPL versus, let's say, the input voltage that you are giving to your transmitter, right? Higher the voltage level, the sound pressure level is going to be higher, right? Of course, it is going to saturate. You cannot keep giving a higher and higher voltage, but the point is, first, we will we'll first create a sound wave, leave it to the medium. So the sound wave is going to propagate from the crystal to the medium 2, and then it is going to be reflected back, and all these reflection coefficients and all that we have dealt with, we know. And so what we can do is, we know when we are generating the electronics sitting here on this side, it knows when I generated this pulse. It knows that, right? And when it is in the receiver mode, when the pulse is coming and hitting back, it knows that this is a pulse that I'm receiving, right? So the electronics can calculate the time between these two pulses, right? And if I know that this is the time between these two pulses, I know the medium that I'm talking of. I know, in which application we are going to put, right? If it's, let's say, for the car automated driver assistance system, I know this is going to be air. So I know what will be the speed of sound, right? And based on the time between these two pulses, right? And if I know the speed of sound, I can calculate what is the distance to the object L, right? So this is pretty straightforward, right? No complications. Any questions here up to this point? So this is what I think I had talked about time of flight, right? So this is what is known as time of flight. So we know that, okay, we generated a pulse and the pulse got reflected. And if I know the time difference between these two pulses based on the time of flight, I can calculate what is the length. So the total time, let's say, is TT. So we have generated, so here if you see, right, we have generated a pulse and the first reflected wave, the time difference is given by TT. So then based on this, I know, and based on the speed of sound, I know I can calculate length, right? So what we need to ensure few things so that this is not messed up. So the first thing that we need to ensure is TW, the window, the pulse that we are actually feeding to the crystal is much greater than the frequency 1 by f. So the sound wave will be having a particular frequency, right? So the frequency that I intend to propagate, the frequency of the sound wave that I intend to propagate, that must have sufficient energy, right? If the energy is not sufficient, then the sound wave is probably never going to hit the medium 2 and come back, right? So we need to ensure that the pulse width should be wide enough. If it's a very small pulse, right? If it's a very small width pulse, right? What does that mean? That the energy or the power content in this pulse will be very small. So that will not even reach the medium 2 and get reflected. So we need to ensure that the TW must be much greater than the 1 by f, I mean the frequency of the sound wave that we are intending to kind of read, right? Also TT, so this is the time between that I allow, the time that is taken by the reflected wave to come. So if we see, this TT must be much greater than TW, meaning if the medium is very close by, what can happen is the reflected pulse will be, so this reflected pulse can move close to this and my electronics will not have sufficient time to distinguish between the pulse that it itself generated and the pulse that was reflected back. So we need to ensure these conditions. TT must be greater than TW to ensure that there is no interference between the generated pulse and the reflected pulse. And also TR must be much greater than TT. So this is the second pulse that we are going to give, right? We are not going to give only one pulse. So we are going to repeat this, right? So the second pulse must be generated after giving sufficient time of having received the reflected pulse. So these are the conditions we need to ensure. Any questions on this? Okay, so we'll stop here for the day today. Tomorrow, I am going to send an email. Tomorrow we will not have the class. This class will be compensated on Friday. I'll send a mail anyway. And next week, Friday, on the week of, on 25th is when we will have the mid-semester exam in the lab session, because that will allow us to have a 2-hour test. Okay. Okay, thank you then.